Good day, I'm Norman Wahlberger. Today I'd like to talk about mathematical expressions and their connection with the natural number frameworks that we've been talking about. So this is a little bit of a subtle issue, and this video is probably going to raise as many questions as answer them. In particular, I'm not going to claim that I have a very satisfactory view of how to effectively create a foundation for arithmetical expressions. We will move somewhat in this direction, but there is much to be done. Okay, so we of course have a rough intuition about natural numbers 0, 1, 2, 3, but we've seen that serious challenges arise once we start moving beyond the familiar view, the familiar range, and moving to bigger numbers. And we've looked at some sort of alternative frameworks that allow us to be more solid about the actual nature of these natural numbers. So we have a view of trying to actually define these things and clearly specify operations and have the possibility of creating proofs for the arithmetical laws. So natural numbers, primitive natural numbers, were regarded as multi-sets of essential strokes on a page. So the strokes were just some kind of elemental unit symbol representing some kind of fundamental something. So for example, this thing here is a primitive natural number. It's a multi-set of these strokes. And we also allowed ourselves this more familiar Hindu-Arabic notation or shortcut symbol for representing this, but we really have this view now that this is actually the gold plate object itself, and this is just a representation of it. Then we saw that we actually wanted to go further and enlarge our view because it's just hard to create really big numbers using this framework. So if we want to create bigger numbers, then we move to the Hindu-Arabic numeral system. And that ultimately involved thinking of m sets of singletons. Singletons being little lists consisting of these natural numbers that we've already defined. So the Hindu-Arabic numerals, or num, rests on a prior foundation of nat. So for example, something like 321, officially now for us, this is really in the context of a vexel kind of situation. So here we have a singleton 0, a couple of singleton 1s, and 3 singleton 2s. And effectively, what these singletons are doing are representing powers of 10. So this singleton 0 is effectively representing 10 to the 0. This thing here is representing 10 to the 1. This is representing 10 2, or 10 squared, 100. Okay. But we can actually work fundamentally just at the level of these singletons and then just interpret things in terms of our Hindu-Arabic numerals. So this is a powerful extension of our natural number system. But now we want to think about going a little bit further. And the reason for that is that both nat and num have limits of applicability, which are naturally induced by the requirement that in order to express one of these numbers, we want to be able to write it down completely and clearly on a page or on our hard drive or whatever we're talking about. So we want to be able to specify these things precisely, and therefore there is natural limits on how big we can express numbers. So in particular, we've seen that, very roughly speaking, the primitive natural numbers are effectively limited in some sense by the rough size of the universe. And so here is 10 to the roughly 200, and it's written in the Hindu-Arabic system. But we're not able to get at numbers that are this big in the primitive natural number system. So we can certainly write it down in the Hindu-Arabic system, as I've done here, very explicitly and concretely. But to write it down in the natural number system is just too much work. Okay, so there's some limits to both nat and, in fact, to num as well. And the Hindu-Arabic numerals are also limited, but by something bigger, not 10 to the 200, but rather 10 to the 10 to the 200. And the reason is that we've seen that there is roughly 10 to the 200 Planck cubes in the universe. So these sort of most elemental kinds of building blocks that you could possibly imagine in terms of writing something down in it. And in theory at least, we could possibly perhaps fill one of these Planck cubes with a symbol, say a digit 0 to 9. So there's 10 possibilities for each Planck cube, and if there's 10 to the 200 Planck cubes, then there's at most 10 to the 200 possible ways of filling out the universe to create some mega huge Hindu-Arabic numeral. So this is some kind of limit on what we can do in our universe. But notice that in order to make this statement, I've had to use this expression here, which is not officially a Hindu-Arabic numeral. Okay? If it was, then it'd be contradictory, because I've just said we can't write down Hindu-Arabic numerals, which are this big. So this represents a mathematical expression which represents some kind of quantity, which is beyond what we can do in the Hindu-Arabic numeral system. So a natural question is, well, what kind of a number is this? Is this a legitimate kind of number? What kind of arithmetic can we build up with objects like this? One of the things that makes this challenging is that there's actually quite a wide range of potential arithmetical expressions that we might want to consider. For example, we've seen just ordinary powers. We've had a look at factorials. We've had a look at sort of these raising or lowering powers. 6, 4 with a bar over it, meaning 6 times 7 times 8 times 9, and 6 to the 4 with a bar underneath it, meaning 6 times 5 times 4 times 3. Then there's towers of exponentials, like this one. There's these higher operations, hyperoperations, like triangle or square, or some of the many higher ones, like star 5 or star n cubed, etc. But there's also then more mundane expressions, things that are not quite so sophisticated and huge as this, but just more elementary things. For example, 5 plus 3. That's also a mathematical expression involving some numbers and operators. Or 16 times 387. Or maybe something involving a summation, like summation I equals 1 to 10 of I squared, which is usually interpreted to mean the sum of the numbers 1 squared plus 2 squared plus 3 squared and so on, all the way up to 10 squared. Or more fancy sort of combinations of various things, like 57 minus 2 cubed, all of that in brackets, times 8 to the 7. So there's a wide range of elementary to very sophisticated kinds of things that we write down, which we generally treat as numbers. But it's really a question about, what the nature of these things really is. What do we really mean? What's the framework for doing arithmetic with these kinds of things? Can we actually concretely, coherently create an arithmetical framework that covers all of these things in a consistent way? It's a very big question. And underlying this discussion is this very interesting question about, should a mathematical expression for a number be considered the same as that number? This is a very important question. So for example, let's consider this very familiar equation that none of us would object to, that 5 plus 3 equals 8. Now if we think for a second, what does it mean? Well, the usual interpretation is that here there's an operation, a binary operation of numbers, and what we're saying is that if we take these two numbers and we apply this operation, then the result of that is 8. So it's expressing this arithmetical identity. And well, we could ask then, does that mean that the two expressions 5 plus 3 and 8 are interchangeable? So is this asserting that if you do a certain operation then you get something? Or is it asserting that this expression and this expression are to be considered completely interchangeable? Those are subtly two different interpretations to what this equality sign really is meaning. So if we adopt the stronger position that this thing is asserting that 5 plus 3 and 8 are completely interchangeable, so in other words, if the answer to this question is yes, then we are in a little bit of a delicate position with respect to a lot of mathematics education. Because then a student, say in grade 2, when given a little test like this, okay, here's a test, I'm a grade 2 student, I've just heard my parents talking about this kind of stuff because they've been watching Wildberger's videos, and so I know that, hey, 5 plus 3 equals 8, it means that they're exactly the same. Alright, so now I go to my test and say, well, here's 3 plus 7. The teacher wants me to evaluate that. Hey, I know how to evaluate that. I'll just write 3 plus 7. Because, okay, I know I could write 10, but why do I need to go through that hassle? Because 3 plus 7 is equal to 10. So this is just as good an answer as 10 is. And similarly, 5 times 9 is just 5 times 9. Arithmetic becomes very simple this way. Of course, we've seen this kind of arithmetic many a time, haven't we? Because this is what the real numberists, I'm referring to that strange mathematical cult that thrived in the 20th century, the real numberists did arithmetic very much like this. Given two real numbers, this is how you add them. This is how you multiply them in general. So we're certainly nervous, okay, about having an arithmetic that really asserts the complete equivalence between these two things. At some level, yes, they are similar or equal, but maybe we would like to, refer this thing here to being a real true natural number, and this is just a mathematical expression that can be evaluated to that natural number. That seems on the whole things to be a somewhat sort of safer position to have. What do you think? So our orientation is going to be that we're going to want to regard mathematical expressions as objects which are separate formally from natural numbers or numerals, but which evaluate to them, at least most of the time or much of the time. So for example, here are some possible approaches to introducing some kind of framework for mathematical expressions. All right? So this is not a proper setup. This is just a possible direction to go, that we might want to go in this direction. So one approach to something, say, that we might call nat expression, okay, is to consider something like 4 cubed. And we can regard this as a shortcut for considering this primitive natural number. All right, so 4 cubed is 4 times 4 times 4. That's 64. And there are 64 little strokes here. All right, so this is the primitive natural number that in Hindu Arabic form we would say is 64. So what we could do is enlarge our names for this thing, so to allow not just 64, written as 6-4 in Hindu Arabic, but to also allow this more fancy, sophisticated kind of expression. So we can think of 4 cubed as being a shortcut notation which ultimately represents that natural number. So that is one possible approach. And we don't have to restrict ourselves to very simple things like this. We could look at combinations. We could say 3 to the 4th plus 2 times 5. Well, that's just a shortcut, a mathematical expression that actually evaluates to this primitive natural number. So here is the true object, and this is now another name for that object. So we're kind of enlarging the possible names that we can give to our primitive natural numbers. So this is one approach. I'm not saying that we're going to do it this way, but this is one way of thinking. And then we could do the same kind of thing, but go up one level to the Hindu Arabic numerals. And we could talk about, say, num expression, where we're now allowing bigger expressions, like maybe 10 to the 32 plus 491. This then could be a shortcut for this Hindu Arabic numeral. So instead of writing this Hindu Arabic numeral out, we could write this thing here and say, yes, this is a suitable replacement or name for this thing here. And there would be some difference between these things because the range of natural numbers is more limited than the range of Hindu-Arabic numerals. So we can expect the expressions that are involved here to be generally possibly bigger, more complicated than the ones involved here. So this is one possibility, to try to regard these mathematical expressions as simply alternate forms for either primitive natural numbers or Hindu-Arabic numerals. So it's an addition to our language that just makes it easier and more flexible to specify largish natural numbers or numerals. That's one possibility. Okay, but what about our favorite big number, z, which is 10 triangle 10 plus 23. 10 triangle 10 being this familiar tower of 10 tens all on top of each other. 10 to the 10 to the 10 to the 10, so on, plus 23. Now this is an expression that we can write down involving the exponentiation, repeated a few times. But what kind of a natural number is this? How does this fit into the framework that we've just outlined? Well, the reality is that it doesn't fit into that framework. Okay, it just does not, because it's too big. This is certainly not a primitive natural number. There's no way that this is a shortcut for an actual primitive natural number, which is a whole bunch of strokes on a page. No way. And it's also not anything representing a Hindu-Arabic numeral. There's no way of writing out a Hindu-Arabic numeral with lots of zeros and then ending in 2, 3 that actually is being represented by this. This is just way too big. So this thing, whatever it is something that really is going beyond nat and beyond num. So the unfortunate reality is that if we're trying to set up a type, say num expression, which is actually independent of natural numbers and numerals, in other words, which aspires to describing objects which cannot be described as primitive natural numbers or as Hindu-Arabic numerals, then we are involved in serious logical strife. We have serious challenges ahead of us, which are not at all obvious how to overcome. So in particular, we have to deal with at least the following kinds of issues. We have to specify what are the underlying objects. Okay? So if the underlying objects are certain kinds of mathematical expressions, then you have to say very clearly what kind of expressions you're going to allow and which ones you're not going to allow, clearly. That's already very challenging. Then you have to define equality. Right? So you have some complicated expression involving all kinds of possible symbols, and then over here there's another one. And natural question is, how do you decide when these two things are equal? So it's a crucial aspect of an effective arithmetic that you are able to effectively decide when two things are equal. And we know that with primitive natural numbers we can do this. We can match up the strokes in one expression with the strokes in the other, and even though it may take us a while, we can systematically go through them and see if they're actually the same size or not. And with Hindu-Arabic numerals it's also straightforward. You just compare digits one by one. With mathematical expressions, this is so much more complicated. And then how do we define the arithmetical operations? Very, very big can of worms here. How do we actually define addition of mathematical expressions, or multiplication, or exponentiation, or factorial, or anything else that we're wanting to be interested in? So we can get a sense that there's very serious problems here, because even our computers run into difficulties at this level. If you explore with your computer system, whatever you have, you just start exploring arithmetic with very big numbers, and you will quickly see that your computer is very capable up to a certain point. And then it doesn't take too much to be able to write down huge expressions like 10 triangle 10 plus 23 and get your computer to do something with that, and it completely balks, just beyond the capability of your computer. And it's not because computer scientists have not thought a lot about this. They have thought very much about this kind of thing. But it's just that the difficulties are so big. So as an example, let's have a look at some sort of mid-level expressions here, roughly around the range of z, not as big as z prime or 3 star n squared 4 or any of those other humongous things that we had. Just relatively mundane things like 8 to the 8 to the 9 to the 7 to the 3 to the 5 to the 11 to the 10, plus this thing, plus this combination. All right, so let's think about that expression. So a first natural question might be, well, there's some arithmetic involved here. Okay, is this kind of the final expression, or ought we to sort of simplify things? Right? It's the same kind of question as 5 plus 3. If you're given 5 plus 3, are you allowed to leave that in that form, or are you obliged to simplify things? So usually with primitive natural numbers or Hindu Arabic numerals, you are obliged and you are able to simplify at least simple additions. If I give you 437 plus 149, you can simplify that. You can actually evaluate that thing and come up with another Hindu Arabic numeral. In this situation here, we are very much more like in the realm of our real number enthusiast friends, right? Where you look at this and you sort of shrug your shoulders and say, I don't know, it is what it is. That's all I can say about it. Okay, and here's another such expression involving some other tower plus some other tower plus some other combination of towers. Okay, so you can see that even doing arithmetic at this level is essentially vacuous. For example, if I asked you, what is the sum of this thing and this thing? All what you could really do is just write down, copy this thing, put a plus sign, and copy this thing. It's essentially vacuous, right? It's exactly the way real number enthusiasts do their arithmetic. In fact, the only kind of question that you really have a chance at addressing really is a much more elementary kind of question. The question of which of these two things is bigger. So, how are you going to decide that? It's a very elementary question. This number, which of them is bigger? Now, because I more or less just wrote them down, I can pretty well guarantee you that they are not equal. I don't know that absolutely for sure, but I'm willing to bet my bottom dollar that they are not equal. And I'm also willing to bet that one of these is vastly bigger than the other, okay, on any kind of reasonable scale. One is just humongously bigger than the other one. But which one it is, I'd have to think about that to get a guess. And if I actually had to, give a good argument for like a proof as to which one is bigger, that might not be so easy to do. So I challenge you, right? See, can you figure out, staring at these two things, which of them is bigger? More generally, can you prescribe some relatively routine algorithm or procedure that, given to largest expressions like this, will evaluate which one is bigger? So we see that arithmetic with this kind of mathematical expression is actually far from being easy. Okay? So we write down things like this and we have a sort of sense of what we're talking about, but that sense actually is not really supported very clearly by anything at all other than a rough intuition. All right, so currently our aim to build a coherent system of arithmetical expressions is not very far off the ground, okay, to be honest. So it's really just a vague, imprecise notion at this point, supported by, well, some examples that we can write down, and a sort of naive sense of bigger and smaller. And really, to be honest, essentially vacuous kind of arithmetic. Right. Now, in other words, it's a lot like the modern theory of real numbers. Okay. So there's a big to-do here, which is to give a coherent account of num expressions that really goes beyond our Hindu Arabic numerals. Okay, and that really says precisely what the objects are, says precisely what the operations are, and gives us proofs of the laws of arithmetic. Very, very big challenge. Now, even though we don't have such a thing, that doesn't mean that we can't still work with these expressions. In fact, we've been doing a lot of work with these expressions because all that discussion of hyperoperations that we had with those star n's and star n squareds and that successor limit hierarchy, that was very interesting. That's really at this sort of stratospheric level. We really don't know what we're talking about here in terms of actually the underlying objects. So we now address more clearly the fact that I've hinted at a number of times, that our underlying natural number system is just not extensive enough to fully support the expressions that I've been writing down in that hyperoperations successor limit hierarchy. We've been writing down these numbers like 3 star n squared 4, writing them down and kind of assuming that there were numbers out there that these expressions captured. But this is all now very much in doubt. I mean, we have to be honest and say we don't really have a theory of natural numbers that extends that far to make really legitimate sense of those things. Now, that's not to say that we can't do some partial things. Okay, we don't have to have a full-blown theory. We can wait a few hundred years, perhaps. Okay, maybe we'll have to do that. But in the meantime, we can still ask questions and do some partial things, as long as we don't start pretending that we actually have a full-blown theory. Okay? We do not want to do like the real number theorists do, is to pretend that there's a solid theory and just never talk about the foundations and just go on pretending. Right? We don't want to do that. Very clearly not. But we can ask still lots of interesting questions, and we can address aspects of arithmetic with these big arithmetical expressions. In particular, we can talk about divisibility. That's a very interesting topic that I want to start talking to you about. The moving towards understanding primes and more generally just how we understand divisibility, even for maybe mathematical expressions which are beyond our usual arithmetic. Interesting stuff, which in a nice way goes back to the ancient Greeks too. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.